Previously, we have introduced integration as the process that reverses the process of differentiation. So the first application that we're going to be looking at now is actually to use integration to reverse the process of differentiation. And the question that we have in front of us is when we are given d squared y dx squared, which is 6x minus 2, and with this we are supposed to reverse back the process to get y in terms of x. Why is it a reverse process? Because in order for us to get d squared y dx squared, we took y, we differentiate it once, we get dy dx, and when we differentiate it again, we get d squared y dx squared. So in order for us to get back y, we are going to integrate d squared y dx squared once, which will then reverse it back to dy dx. And we will take dy dx, we integrate it another time to reverse it back to y. So let's try this. We have d squared y dx squared that is given to us as 6x minus 2. We're going to reverse the process to get dy dx by integrating d squared y dx squared. So we will be integrating 6x minus 2. So integrating 6x minus 2, it is going to be 6 here, it is going to be this square divided by 2, minus integrating 2, it is going to be 2x. Then let's not forget about the arbitrary constant plus c. So this is equal to 3x squared minus 2x plus c, and most of the time the question will give you the kind of condition that will allow you to solve for the arbitrary constant. So in this question, it did give us, the question says that the gradient of the curve at the point 2 minus 9 is 3. So gradient is dy dx, which means that at the point 2 minus 9, dy dx is equal to 3. Let me write it down. So at 2 minus 9, dy dx, this is equal to 3. X is equal to 2 at this point, which means that for dy dx, it is going to be 3 times 2 squared minus 2 times 2 plus c. This is equal to 3. This will help us to solve for the value of c. c is equal to minus 5. So therefore, now we know the expression for dy dx. dy dx is going to be equal to 3x squared minus 2x minus 5, and our job is not done because we are supposed to have y in terms of x. So we need to reverse this once more. So to reverse this to get y, we will integrate dy dx, which means that we will be integrating 3x squared minus 2x minus 5. So this will be 3 times of integrating x squared, it is x to the power of 3 over 3, minus 2 integrating x is x to the power of 2 over 2, minus 5x, then plus arbitrary constant, so plus c, which means that I will have y to be equal to x to the power of 3 minus x squared minus 5x plus c. We still need to solve for this second arbitrary constant, and I'm going to make use of the same condition, which is the point 2 minus 9. This is the point when x is equal to 2, y is equal to minus 9. So when x is equal to 2, this will be 2 to the power of 3 minus 2 to the power of 2 minus 5 times of 2 plus c. This is minus 9. This tells me that c here is going to be equal to minus 3. So the question is solved because y is now x to the power of 3 minus x to the power of 2 minus 5x minus 3. Another way that we can be tested in making use of integration to reverse the process of differentiation will be a question that looks similar to this. Okay, first we will be asked to differentiate, and with the differentiated result, instead of using standard results to integrate, we're going to make use of the idea to integrate. Okay, a question that is like this. Let us give it a try. So the first thing that we need to do in this question is to differentiate. So we are given that we are supposed to differentiate this square root of x divided by 1 plus 2x. And to differentiate this, we are going to make use of the quotient rule. So this is going to be equal to 1 plus 2x, and we are supposed to differentiate the numerator. For the numerator, why is this? I can rewrite it as x to the power of half. So differentiating this, it is going to be half x to the power of half minus 1, which is minus half. Then minus away, writing down the numerator, which is square root of x. Then I'll differentiate the denominator. 1 plus 2x, when I differentiate it, I'm going to be getting a 2. So this is going to be divided by the denominator square. So I will have this. For the numerator, let me rewrite it. It is 1 plus 2x divided by 2 square root of x minus this is just 2 square root of x divided by 1 plus 2x square. But the question wants us to prove something that is more similar, something that is like this, okay? So I'm going to manipulate this further. I'm going to try to group this numerator here into one single fraction. And to do that, I'm going to take this second term here, and I'm going to multiply the numerator and the denominator by 2 square root of x over 2 square root of x. So for the denominator wise, now we will have the same denominator, and as for the numerator for the other side, it is going to be minus 2 times 2, 4, square root of x times square root of x is going to be x divided by this. Okay, I have this divided by 1 plus 2x square. So for the numerator wise, this can be now grouped into one single fraction. It is going to be 1 plus 2x minus 4x divided by 2 square root of x over 1 plus 2x square. And now this is 1 minus 2x over 2 square root of x, and this is going to be divided by 1 plus 2x square. And now we can rewrite this into the form that the question wants us to show. It is going to be equal to 1 minus 2x over 2 square root of x, then 1 plus 2x square. Okay, we have shown this first part, and the question wants us to hence, okay, hence we are supposed to evaluate this. And please take note that for this that we are supposed to be integrating, there is no standard results, there's no good manipulations that we have discussed previously that will allow us to integrate this. But the good thing is we are going to make use of the process of differentiation to integrate and try to reverse the process, okay, so that we can get something that is like that. So since when I differentiate this, I'm getting this, which means if I were to be integrating this, so if I were to be integrating this, 1 minus 2x over 2 square root of x and 1 plus 2x square. If I were to be integrating this, we should be getting back a square root of x over 1 plus 2x plus c. But this, again, it is not what the question wants. The question wants a definite integral. Integrating from nothing to nothing. It is integrating from, according to what the question says here, 1 to 4. We are supposed to integrate it from 1 to 4. So using this as our inspiration, I'm going to write down this, integrating from 1 to 4 of this, which is actually this expression here. So 1 minus 2x over 2 square root of x, 1 plus 2x square. This is going to be equal to square root of x over 1 plus 2x from 1 to 4. So this 2, I can take it out of the integration notation. It is going to be 1 over 2, integration from 1 to 4 of 1 minus 2x over square root of x, 1 plus 2x square. Okay, and you realize that this integral over here is what the question wanting us to evaluate. So we already gotten this here. This on the right hand side, it is going to be, I will just evaluate this part. So it's going to be square root of 4 over 1 plus 2 times 4, minus away, substituting 1 in, square root of 1 over 1 plus 2 times 1. So this 2, I'm going to bring it over to the other side, and on the left hand side here, it is going to be integrating from 1 to 4 of 1 minus 2x over square root of x, 1 plus 2x square. So since 2, I multiply across to the other side, it's going to be 2 times of this. This is going to be 2 over 9. Minus this is 1 over 3. So my answer here is minus 2 over 9. But the most interesting thing about integration that I find is actually making use of integration to find areas. Let us look at the next application, making use of integration to find areas for scenarios that are like this, this, and this. So if we were to have a situation that is like this, where we are looking at a region that is bounded by the curve, the x-axis and 2 vertical lines, x is equal to A and x is equal to B. This region here, if we are not able to apply any of the standard results, for example, area of triangles formula, area of rectangles formula, area of trapezium formulas, we are not able to apply any of these standard results to evaluate, and we possess the equation of the graph, then this area can be found through integration. It is when we try to do a definite integral, integrating it from A to B of the expression of the graph that is given to us, dx. So we are integrating with respect to the x-axis. This will actually give us the exact area that is bounded by the curve, the x-axis, and the 2 vertical lines, A and B. And if I were to have a situation that is like this, which is an area that is bounded by the curve, the y-axis and two horizontal lines A and B, it is the same as this, which will now be integrating from A to B of the function, but this time the function is supposed to be expressed in terms of y, then dy. But one thing to take note of is if the region happened to be in the negative y-axis part, like for example this, okay, previously the region is in the positive x-axis side. Sorry, positive y-axis side. So now if it is in the negative y-axis side, if we were to just integrate it from A to B of the expression of the curve and dx, this is going to give us a negative area because it resides in the negative y-axis region. So in order for us to find the area of a region that is like this, we need to add in an additional negative in front, okay, just to convert the negative value that we have gotten into a positive area. The same goes for the case where the graph or the region happened to be in the negative x-axis side. Okay, previously this region is totally in the positive x-axis side. Now if it is in the negative x-axis side, the region that is bounded by the graph, the two horizontal line and the y-axis can be found by using integration. It is negative of integration from A to B fy dy. Again, it is the same explanation because for a region that is like this, when we are integrating it, we're going to get a negative value. It is the negative of the area. So we need to add a negative in front to make sure that the area that we are finding is a positive value, which means if you have a situation that is like this, okay, where we have a curve and we are looking at the region of we are looking at the area of the shaded region. So for this region here, it is positive. For this region that is below the x-axis or in the negative y-axis portion, this region here is going to be negative and this region here is going to be positive. Okay, so we cannot just simply integrate it from A to D to find the area. For this case, we need to break this up into three parts. So the positive part will be from A to B because it is a region that is in the positive y-axis. That is why I'll integrate from A to B of fx dx. And because we acknowledge that this region here is going to be a negative area, we need to cut it out, or we need to focus on it, and we try to integrate it from B to C, and we need to add a negative in front of it to make sure that we are looking at it as an area, a positive number. So we'll work on this. Then after that, I'll add to integrating from C to D of this again because it is a positive region. Okay, it's a region that is above the x-axis, it's a region that is on the positive y-axis. So when we carry out a process of definite integral, it is going to give us a positive value. Let's take a look at some examples. Let's take a look at this, okay? We're supposed to find the area of the region that is bounded by the curve, the line x is equal to 0, and the x-axis. So the curve is basically this region here. Let me just do a quick sketch of it. So we have this, okay? And we have this, and the region that we are interested in to find the area of will be this region from x is equal to 0 all the way until this value, which we do not know, so we better try to evaluate it using what we have learned previously. This is y is equal to 3 plus 2x minus x squared. So to find this, we are going to let this 3 plus 2x minus x squared, we are going to let this be equal to 0. So factorizing this, it is going to be x plus 1 and 3 minus x. This is equal to 0. So x is going to be equal to minus 1 or x is going to be equal to 3. Minus 1 will be here and 3 is going to be this, and this is what we are interested in. So applying integration to find this area gives us this. The area of the shaded region is going to be integrating from the lower limit, which I'm going to go for 0, to the upper limit, which I'm going to go for 3, from the left-hand side to the right-hand side. So 0 to 3 of the expression of the graph in terms of x dx, okay, with respect to the x-axis. So dx. So this will give us the exact area. Okay, this will give us the exact area of this region. Okay, it is simply amazing what integration can help us to do. So this integrating, it is going to be 3x plus 2, this will be x squared over 2, minus integrating this is going to be x to the power 3 over 3. And we are integrating this from a lower limit of 0 and an upper limit of 3. So it is going to be equal to 3x plus x squared minus x to the power 3 over 3 from 0 to 3. This will be 3 times 3 plus 3 squared minus 3 to the power 3 over 3. This minus away, if I were to substitute 0 in, the whole thing will be 0. So the actual area is going to be equal to 9 units squared. And this that we have here, we are looking at a region that is on the positive x-axis side, and we are supposed to find the area of this. So we have discussed about this. We are going to try to look at 2 by using the process of integration. And to do this, we are going to integrate this from the lower limit. I'm going to go for 1 from the bottom to the top. Okay, so the lower limit, I'm going to let it be this, -1, and the upper limit, I'm going to let it be 2. So from -1 to 2. And for the expression that we have here, too bad, this is y squared is equal to 2x minus 1. So we are not ready to start off our process of integration, because according to what we have discussed here, when we are trying to do this version, it has to be in terms of y, because we are going to be integrating it with respect to y. So what we are going to do, it is a simple step. We are going to try to take this equation here, and we're going to make x the subject. The equation that is given to us is this y squared minus 2x minus 1. So, this is equal to, y squared is equal to 2x minus 1. So we're going to make x the subject. So this is 2x is equal to y squared plus 1. So x is going to be equal to half of y squared plus 1. And now we are ready, because what we are going to plant in here is going to be a half of y squared plus 1, then dy. So let's try to integrate this. Half is a constant. I'm going to take care of the integration notation. So it's going to be this y squared plus 1 dy. So we have a half. Integrating this, it is going to be y to the power 3 over 3. Integrating this, it is going to be y from -1 to 2. This is going to be equal to half, and if I were to substitute the numbers in, it is going to be 2 to the power 3 divided by 3 plus 2. Then minus away, substituting this in, it is going to be -1 to the power 3 over 3 plus this is -1. And if I were to, this is a curved bracket, and if I were to substitute this, if I were to evaluate this, this is going to get us a 3 units square for the area that is constant in this question number 2. Let's take a look at question number 3 here. Okay, a region that is actually in the negative y-axis region. So for question number 3, because it is a region that is in the negative y-axis region, so we will be expecting that if we were to find integration from 2 to 5 of this minus 12 over x squared. If I were to just do an integration for this alone, the answer that I'm going to be getting is going to be negative, because it is in a negative y-axis region. So for area of this particular region, we are still going to be making use of integration, but like what we have previously discussed, we need to convert this into a positive number to represent area. So because this is negative, so I need to add in this extra negative in front. So I'm going to factorize out minus 12, which will give me a positive 12, which means that we will be integrating 1 over x squared. And for 1 over x squared, I think I'm going to just further re-express this as x to the power of minus 2. So this will be 12. Integrating this, it is going to be x to the power of minus 2 plus 1. It is minus 1 divided by minus 1 from 2 to 5. So we have a 12. And this is minus 1 over x from 2 to 5. So we have a 12, and it is going to be minus 1 over 5 minus 1 over 2. So my final answer here is going to be equal to 18 over 5. Let's look at a slightly interesting situation. It is a situation that is like this. For this situation here, it is a region that is between two graphs. Can you see that it is between two graphs? One graph is definitely this, okay, this is pretty obvious. The other graph is this line here, this horizontal line here. So it is the area that is between two graphs. So to find this area, of course, we can try to cut this up into small little pieces. For example, I can cut it up here, and I can also cut it up here. So I'm going to attempt to use integration to find this region. How do we find this region? I'll take the area of the rectangle. Then I'll minus away this region here, which I'm going to be making use of integration, because integration specifically can only help us to find the area that is between the graph and the axis. So integration will not help me to find the area of this region. Integration can help me to find the area of this region here. So I would need to take the big area, minus away the small area to get this part. And I'm going to do the same for the rest of the parts of this region R. And this is going to be pretty tedious. So there's a good way, a good strategy to overcome something that is like this when we are dealing with the area that is between two graphs, the area that is bounded between two graphs. In our outline, I've indicated it here. to find the area that is between two graphs, we just need to do an integration also. We need to spot our lower limit, we need to spot where's the upper limit, and we will take the top graph minus away the small graph within the integral, just like this. Okay, so it is integrating from the lower limit of a to the upper limit of b. Then we take the top graph, which is fx in this case, minus away the bottom graph, which is gx in this case. And please take note, when you're applying this, this is independent of the position of the graphs. That means the region that we are trying to find area, this region can be entirely above the x-axis, it can be entirely below the x-axis, or like in this case here, it can be partly above and partly below the x-axis. But regardless of the cases, it is always going to be integration by taking the top graph minus away the bottom graph. Okay, so let's try to apply it to this particular question over here. So for this situation, the first thing that we want to do is to identify the equation of the top graph. This happened to be a horizontal line, so it must be y is equal to some number. And to do that, I'm going to just substitute 4 into this to get the corresponding value of the y coordinate at this point. So when x is equal to 4, y is going to be equal to 4 squared minus 4. Y is equal to 12. That means this line here is y is equal to 12. So to find the area of this region R, this shaded region here is the region R. So to find the area of this region R, we will just need to do an integration from the lower limit, which is going to be minus 4, to the upper limit, which is 4. And I'll take the top graph, which happened to be just 12, okay, a constant 12, minus away the bottom graph, which is going to be x squared minus 4. So let's work this out. This will give us the exact area of this region here. So this is going to be integration from minus 4 to 4. 12 plus 4, this is going to be 16 minus x squared dx. So this is equal to 16x minus this is x to the power 3 over 3 from minus 4 to 4. So this will be 16 times 4 minus 4 to the power of 3 over 3. This is when I substitute 4 into the expression. Minus away, this will be 16 minus 4 minus minus 4 to the power of 3 over 3. And if I were to calculate this, the area is going to be 256 over 3. And that's all for integration, the application of integration. And I'm going to see you in the next chapter.